Well, good morning, good evening, everyone. Welcome to SETI Live. We have a crowded screen today. Good morning, good evening, everyone. Welcome to SETI Live. So we seem to have an echo there. Hopefully that will be cured. Sitting beside me is Jeonghee Rho, a colleague from the SETI Institute. We're also joined by Danny Milisavljevic. I could almost, we practiced that. And Ilse de Looze. Danny and Ilse, tell us where you're tuning in from today.
Hi, I'm coming from Purdue University in West Lafayette, Indiana, where I'm an associate professor.
Great, thank you. And Ilse? Hi, Ilse. Where are you tuning in from today?
Ilse, could we?
Hi, Ilse.
You're out there.
Where are you tuning in from today?
From Ghent University in Belgium.
Great, thank you.
Ilse,
I think we have a little bit of a delay coming in from the audio here, so we'll take that into account as we move forward. Thank you, everyone, for joining us. We're going to be talking about an amazing object, Cas A, in a moment. But please, if you have any questions, pop those into the comments section, and also let us know where you're tuning in from as well, because we'll read that out as we move through. And we'll certainly be talking about where you're from and asking your questions to the experts today. So I just want to start by introducing, or we're going to introduce the object we're so fascinated by, Cas A. It's called Cas A because it's in the constellation of Cassiopeia, which is the big W in the sky if you're in the northern hemisphere. And the letter A is because it's the brightest radio source in that constellation. But we're not going to talk radio at the moment, are we? We're talking infrared. So Jeonghee, if you'd like to start, tell us a little bit about Cas A. What is it?
Cas A is the youngest supernova remnant in our galactic plane, and it is exploded about 340 years ago. So especially it has a lot of ejecta which may be produced by nuclear synthesis. So argon and silicon and sulfur, all elements basically. This is the place creation of a heavy element in the universe.
Okay. So a massive star that exploded, that the light from that star traveled. How far away is it?
3.4 kiloparsec.
Okay.
So 9 light years. Yeah.
So about 11,000 light years. So it went off 11,000 years ago. The light has traveled 11,000 years, plus about 340, and then around 1690, that light arrived at Earth, which is really cool. Yeah. Danny, this is we said the youngest supernova in our galaxy. How common are these things exploding? How rare is Cas A?
Well, I can answer that in two ways. Generally, in the universe, there is a supernova that explodes once every second. So I like to joke, if you listen closely, maybe you can hear them going off. Not really. Many of them, the majority, are too far away for us to observe. Okay, but if we're talking about in our own Milky Way galaxy, galaxies like those, on average, should have an explosion once every 100 years. Okay? As Jeonghee mentioned, Cas A explosion, with respect to when the light first arrived here, was about 350 years ago. We're actually overdue for another supernova of that variety, of one that comes from a massive star.
Okay. And I know Betelgeuse, people would love that as the candidate, but we'll leave that for another conversation. Fingers crossed. So maybe we can bring up an image of Cas A, one of the images from your publication, and we can have a look at this. And this shows the sort of the chaotic structure. As you imagine, an exploding star is pretty chaotic when it falls down to it. It's a mess.
And beautiful, but chaotic. Yes.
Beautiful mess. A piece of art more than science in some ways. I wondered if you could talk. There's a lot of information on this image, both in terms of labeling and in terms of colors. Could you talk a little bit, without going into specifics just yet, about this image and what we're looking at?
Oh, I'll give the turn to Danny.
Sure, I'll just take a little bit. You see my name on the bottom there. So yeah, first of all, let me put into context what you're seeing in front of you took approximately 7 years of effort from our team. Okay, I was the PI, but there were so many people that were involved with this project. This picture itself comes from the paper that overviews the survey, and there are multiple sciences that stem from that, including Jeonghee's, which we're focusing in today. Okay, so that's where it came from. What are we looking at? These are the exploded guts of a star for us to investigate. The arrows are pointing to different parts. The ring that you see, that the arrow points to reverse shock ejecta, that's the bulk of the star stuff that's been ejected into various directions. It's been heated by a shock wave that develops as the supernova interacts with surrounding gas that was shed by the star before it exploded. Okay? And that stuff, that circumstellar stuff, the stuff that's shed by the star before explosion, is the other arrow that reached shock material by forward shock. And that's actually of a different composition. And here you see it glowing in that orange and red because it's a cooler temperature compared to the, as depicted here, white hot reverse shock ejecta. Okay, and then one more thing, just the big surprise from this image, we kind of expected the forward shock, reverse shock, but you see that green thing in the center, that green monster that we called it, that was one of the surprise discoveries of the survey. And that ends up being related to the mass loss by the star before it exploded.
Okay. Just to clarify as well, we've got a bunch of colorful numbers in the top right. And this is talking about the wavelength of the light that we're looking at, isn't it? Can you, Jeonghee, can you say a little bit about what those
first,
mean?
Yeah, I want to mention this is the James Webb images, so you can see very detailed. So for example, green is F12 ATW, it's 12.8 micron images. So that's the, show the wavelengths in, you can, by 100, then it will be microns. Yeah, 12.8 microns, 21 microns in long wavelengths, which is showed highlighted by red emission at the edge. Those are continuum heated by the shock.
Okay, and so this is an infrared image, isn't it? It's these wavelengths because JWST is an infrared telescope. We're looking at sort of a heat image, and these are not real colors. They're real, but they're not real.
Right. If you have seen the infrared camera, it's basically heat sensor. We use a lot in many places now. If you go enter the new room, especially bathroom, it lights come up. They sense the heat from our body. That's the, it traces the different wavelengths, but that's the basic idea.
Yeah, if I can chime in, there's a little bit of a delay, so sorry about that. But so all of the images that you can see here, a lot of them are dominated by dust emission. For instance, the last one, the 25.5 micron, is very evident from the circumstellar dust emission that you can see around the remnant. But then if you look at the white color, which is a combination of the 7.7 and the 25.5, is not so much dominated by dust, but you have some special lines that are dominating in that broadband, such as argon lines or oxygen lines. And you can see in particular the white or pink-like colors are coming from the ejecta and all the ejecta shrapnel that you can see in there. And then the green is coming from the green monster, and that's again dominated by circumstellar dust. that peaks at around 12.8 micron. But all of the dust has quite warm temperatures of 100 Kelvin and above.
Okay. We're going to come back to the definition of warm in a minute and what we mean by dust. But I'm just going to call out to some people who are viewing. Freddie's from Texas. Welcome. We've got Utsaf from India, Sweden, Central New Jersey. Hello from the Nordics. Lincolnshire in England, Warsaw, Toronto, South Bend, Italy. So thank you, everybody, for tuning in around the world. That's wonderful. Jeonghee, I interrupted you. You were going to add something to that.
Oh, I was just want to mention that green monster we call the green emission in the front. Those are green monster. The Looze is leading the paper submitted, but that's very new from the James Webb images. Basically, you know, the Eta Carina, for example, it has a lot of circumstellar medium. That's the one we believe that exists in pre-explosion of supernovae.
Okay, so let's focus in on the green monster as it's, and again, it's green because of the color choice of this, because this is it's a beautiful shade of, actually it's a strange shade of green, but it's a green nevertheless. This is dust, you're saying. Could you say, I mean, you know, you expect supernovae to throw out elements and stuff. What is this dust and where does it come from?
So this is actually material that was lost by the progenitor star before the supernova exploded. So this has likely taken place, mass loss, at around 10,000 years or so prior to the explosion. And indeed, during the mass loss, metals are also expelled in stellar wind. So part of the material is enriched with metals. And from those metals, if you're far enough from the star, the material can cool down and you can start forming first molecules and in the end, bigger molecules, which we call dust grains. But you have to reach low enough temperatures to be able to do that. And that's actually what we're seeing right now. And why are we seeing it right now? Well, the original blast wave of the supernova is gradually traveling through space and is now in different directions, picking up on some of the material that was lost prior to the supernova by the progenitor star. We're actually looking back in time what the history of the progenitor star was before it went supernova. And that's very interesting because the green monster is also telling us that there must have been very asymmetric mass loss. And that may then again point to the fact that there was a sort of binary star involved, that it was a binary system that could have caused an ejection, eruption that occurred on one specific site only. Because we don't see any evidence of a counterpart for the green monster on the other side of Cas A.
Yeah, if I may add something to that. Sorry, Simon, but this is a part, I get a little upset with the green monster ultimately, because one of the main goals of our Webb observations was to try and understand how the star exploded. A bomb went off, and I want to see material closest to the ignition point. Okay? So I want to look deep in the heart of the star, and that would be basically in the center of the ring that you see. So when we first got the Webb observations and this wall of emission, later to be color-coded in green, that came to be green monster, we thought was maybe associated with the insides of the star closest to where that explosion took place. Okay, but actually through a lot of work, Ilse's work, Jakob Vink, and many other collaborators, we came to understand that it's a projection effect. The green monster is actually photobombing our attempt to see it inside. So this wall of emission is actually between us and the inside of the supernova.
So basically, there are two ways you can tell difference from this ejecta, which is pink-white, and green emission. One is the velocity. This ejecta is like a few tens, 10,000 kilometers per second. But this green monster, which is existing dust, is only a few hundred kilometers per second. Another way is abundance. This ejecta is freshly made heavy element. So it has a highly enhanced abundance, while this green monster is not too far from solar abundance.
Okay. So it's basically that stuff was puffed out when the star is in its last few happy days of being a red supergiant.
That's right.
And
maybe not so happy. Yeah, but that's right.
And this stellar wind is blowing out at a fair pace, but not huge. And then you get the supernova material, as you say, about 10,000 kilometers a second, which is insane when you think about how fast that is coming out. And that just rams into the stuff that was floating around, that was given out before the star exploded. Okay.
Right. Yeah, if you see details in there is a lot of holes. We just wondered what they are. Actually, we think this ejecta material is pulling, going through those circumstellar medium materials. So they made the holes.
Could we have a look at that slide and zoom in on that green monster? I think there is an image of that. Yeah, here we go. So here you can see the whole remnant on the left, and zooming in on the green component, and it does have these holes. Say again, what do you think they are?
Oh, they are basically this ejecta material which has 1,000 to 10,000 kilometers per second velocity. Then it's going fast, going through this material that made the holes.
Right, so sort of bullet holes.
Yeah, bullet holes. That's exactly right.
Shrapnel. That's right, like shotgun shrapnel.
Yeah.
Ilse's can discuss a little bit more. The exact mechanism is still to be verified, but it comes down to some kind of interaction between that ejecta and the blast wave and the material that's there.
You can see here the holes.
Yeah, that's weird. Absolutely amazing. Yeah. That really is.
There are a few mechanisms in the universe that can make such round things. Right?
So we're going to come back to more of your observations in a moment, but of course this is quite close by, 11,000 light years. It's in our own galaxy, but you can use this supernova remnant to think about what's happening in the very early universe, can't you? Because when you go to billions of light years away, you can't make out individual stars, but you would like to know what's happening in the early era of star formation. Say a little bit about how Cas A is a wonderful model for what happened in the early universe.
So one of mysteries started when a lot of dust abundance is observed from high redshift galaxies, which is early universe, about 500 million years ago, right after Big Bang. So that's only time, that AGN, the other low mass stars, didn't exist yet. So only high mass stars, first stars has born. So this is Cas A is analogous to those massive stars in the early universe. So the amount we observed from the Cas A, we can infer the amount of dust mass in the early universe from combined with the Spitzer and Herschel, we all together work together and indicate that the mass is sufficient enough to explain the early universe. And however, before James Webb, we didn't know the exact process, how they make that dust. We showed some carbon monoxide molecules. It cools down through the molecules such as carbon monoxide. So we'll show that.
Okay. So in the early universe, there's the James Webb, which can actually image some of these very as most people know, as you look out in space, you're looking back in time. So if you're looking a long way away, you're looking back to the early era of the universe, and you're seeing a lot of dust. And dust wasn't made in the Big Bang, so it has to come from somewhere.
Right.
And this is an explanation for how all this dust is coming to be, because you have the ancestors of Cas A. working hard in the very early universe to make all that dust.
Right. So
That's
I mean,
an excellent. Oh, go ahead. Sorry.
Yeah, go ahead, Danny.
No, I was just gonna say it's an excellent description, Simon. I go a little bit further, is just to say, if we're gonna have any chance of understanding galaxies at the edge of the universe, we need to know what's happening in our own backyard, right? And something like Cas A provides a very detailed analysis that provides the science and the measurements and the calibrations needed to understand things very far away. There's a lot of stories in the past couple of years about Webb observations of these early galaxies breaking theories, right? Breaking the universe as well. Those conclusions come from simulations that need to make assumptions about the energy input from supernovae, the dust that contributes from them, the nucleosynthesis yields, right? And those assumptions are based on the kind of work that we're doing here on Cas A.
Mm-hmm. Excellent. So we mentioned, thank you. We mentioned carbon monoxide. We're going to come back to carbon monoxide in a second, which of course not a good thing to have in your basement in your house, but is very important in space. Just going to call out, we've got listeners, viewers from Budapest. We've got them from Argentina, and New Hampshire, Luxembourg. So welcome everybody. So carbon monoxide is a very important gas molecule in supernovae, well, in the universe in general. Say a little bit about carbon monoxide, where it comes from, and why it's important in Cas A.
So supernova make a lot of heavy element as well as light element, which has the carbon and the oxygens. So you combine together, make a good coolant. So when it combined, it take the energy. So it take the cool the temperature of the gas to lower temperature. So that is leading to dust formation. Without carbon monoxide, this hot gas, which has X-ray gases as well, has 10 million degree, would not be able to cool down to the dust temperature, which formed around 1700, the highest temperature to 1000 K. So that's why seeing this carbon monoxide is very important. It's not the pre-existing dust. What we are seeing is actually making new dust. So that's the important concept come from this detection of the carbon monoxide.
Okay. Now, you were using the image we saw. This is imaging. You were also using spectroscopy to look at Cas A. We haven't got time to go in too much.
Yeah, let's go to
sort of quick peek.
Slide down to colorful one, green. Can we go this image? Oh, here it is.
Yeah,
That's great. So this another green emission colored in carbon monoxide. Then argon ejecta and synchrotron emission. So we can see, basically, surprisingly, CO is everywhere in corresponding to the ejecta. So wherever you see the ejecta, and CO cooling down to form the dust. So everywhere, little knots has all those the gas and molecules and dust at the same time. Can we go next slide? Two down, the spectrum. Oh yeah, this is the carbon spectrum. This is very detailed band we call the headband. So you can see this is rare detection only or possibly with using the James Webb. Basically, there is a lot of carbon molecule is complicated, right? As you know, then there is a lot of rotational levels. Each rotational level has a vibration level. So, for example, rotation level has 100, then vibration another 100. So it's like a few thousand lines combine together, make this sinusoidal patterns. So we can diagnostic this spectrum and infer the temperature and density. So its density is very high, 10 to the 7 to 8. Temperature is actually we found two temperatures like 1,000 degree and like 45,000 degree, which come from many interface with gas and
So these are quite complex. Spectroscopy can be complex sometimes. This is more like a sort of an audio file than a spectrum, isn't it? And this is because if you have a molecule which are two atoms joined together, they're doing all sorts of things. They're vibrating, they're spinning, and so it's almost producing sort of this music in light.
Right. Like the music patterns and artificial, drawings, kind of.
Yeah, I'd add here to really appreciate the beauty of these observations, you need to compare it to others, and the closest others would be other galaxies, supernovae happening in other galaxies, and you do not get this resolution. Okay, everything's smeared together, and then the noise is much. There'd be no way to model to this detail, and you see on the bottom there, she's comparing to Orion, and you can actually see, which is really nearby, right nearby, and so you can. There's tremendous science that you can gain from these observations made possible by James Webb that we haven't been able to do before.
Yeah,
so you can see Cas A is much stronger than has a little broad continuum underneath, which is due to the high velocity of the Cas A.
Right, because it's a supernova remnant.
Right.
And as you say, Danny, when you're looking at a distant galaxy, you're not looking at an individual supernova remnant. You are looking at a cluster of thousands of stars in various points of evolution, maybe a few supernovae going off within them, and to separate all of that stuff is not easy.
Well, it depends on the scale. Sometimes we can isolate a supernova remnant. Okay. Within the galaxies that are not too distant. But certainly when you get so far away, all that emission blurs together. Absolutely. And you have to start making assumptions about the families.
So we have a few questions. I know we're running a little bit short on time, but this first one from Mathematica. I read somewhere that Cas A is the brightest radio source outside of our solar system. If this is true, what is emitting the radio signals? So
it's true indeed. It's the brightest source outside of our solar system, and it's synchrotron emission that is dominating the radio emission at those wavelengths. It's because you have charged particles that are spiraling around magnetic field lines. So because you have a supernova, and because of the shock wave, so that the blast wave, all the energy that is released creates this sort of shock wave that is sweeping up material, and it's also compressing material. So if there was before a magnetic field, you will get a stronger magnetic field because you also have a lot of all the gases all ionized, so you have a lot of charged particles, and you create a very strong magnetic field, which creates also a lot of synchrotron radiation, what you can pick up at these wavelengths.
So basically, that radio morphology is similar to the blue emission I showed at short wavelengths, 2.5 micron. So which is synchrotron showed a very linear correlation from radio to 3.5 micron.
Okay, great.
I encourage your listener to look up the story of Grote Reber, an amateur astronomer who built a radio dish in his mother's backyard, who discovered Cas A. Cas A, Cassiopeia is the constellation. A is the brightest source in that constellation.
Yeah, cool. Thank you. Okay, black holes are bound to come up in conversations with supernovae. From Utsav, is the supernova of a star needed to form a black hole? So is there a black hole here, and is this the way you make them?
This is the way. Oh, yeah, go ahead, Jeonghee.
Go ahead. Yeah, you or Danny can answer that.
Well, indeed, you need an explosion, but it's only for more massive stars. And then in this case, in the case of Cas A, we form a neutron star. But if a star is even more massive, then you can get a direct collapse of a black hole. Then the core of the star will not be able to resist gravity anymore if it's heavy enough, and it will collapse to a black hole. But that's only occurring above certain masses. Typically is assumed around 40 solar masses. So if the star had an initial mass that was 40 times heavier than our own sun.
What was the mass you estimated a progenitor star for Cas A?
Between 15 and 25. So there's quite some range. We don't know exactly.
Nobody was there. And the only caveat to this,
not anymore anyway, no.
The only caveat I'll add to this is that, the rules may have changed slightly at the beginning of the universe. There's a lot of interest in understanding how the galaxy is assembled and their central supermassive black holes and the pathway to that. But generally, in the universe as we know today, yes, you need the pathway of a supernova to get to the black hole.
Okay.
Cool. So yeah, remnant of the point, the point source is seen in only X-rays. So it's not the progenitor, the compact source of the Cas A is neither typical neutron star or nor black hole. It's kind of a warm point source from X-rays. We believe that's the compact source. But so that's very rare. We don't completely understand that type of a neutron star yet.
Yeah. Okay. Jake asks, what type of star was it before it went off? So we have a rough idea of the mass.
Yeah, it's right. I mean, it used to be people believe it's ultra stars, but more mass is going down 1525. So it's a red supergiant is another hypothesis. Do you have more opinion on that?
I just add what we do know can come from light echo spectroscopy. What's that? So people have actually taken spectroscopy of the light from the original supernova. So as we said, about 350 years ago, the light that took a beeline straight to us arrived on Earth, okay? But light goes in all directions from a supernova, and it can bounce off some kind of dust sheet. And because light has a finite velocity, it just takes longer to go in that direction and then come to us. So very clever people have detected these and taken spectroscopy and be able to compare it to other supernovae to help with the classification. And from that, we know that the star was largely stripped of its hydrogen envelope at the time of explosion.
Okay.
So basically, it has layer of the element, heavy element inside, the lighter hydrogen and helium outside. But by some reason, binaries or some other pulsar activities, it take off those, strip off those outside layer of the hydrogen helium. So those are big question in the supernova community. We thought originally was a heavier mass, like 30 solar mass, but more and more people think it's evidence is toward really lower mass, like 15. So that's the big area in debate.
Okay, great. Thank you. A good night sky object, though, would be Betelgeuse, if you're looking for maybe, what will end up at some point. We're just going to wrap up with one question, and this going back to these holes in the green giant. They appear to be round. Does that mean they're all facing us? This is all perspective.
That's a very good question. I don't know if you can still put the slides up. I don't know if anyone added if the figure is there with a zoom in on the holes, or otherwise you can show maybe the figure with the holes.
Yeah, that's great.
Yeah.
Yes. Yeah, indeed. They all seem to be facing us. Well, one thing is that probably what we're sensitive to is only a very thin sheet of material. It may be because it originally was a very thin sheet of material that was lost by the star, or it may be that the dust that we're seeing is actually being destroyed. If you have a sheet of material and you get a bullet that goes through it, it sort of creates a shock wave. You can compare it to a stone that you would drop in a pond. You would also get this kind of shock wave. In a similar way, that this is what's happening, that creates this sort of ring structures around it. And indeed, it's actually something that is still puzzling us. There is an example that we show in our paper where it's not directly, so it doesn't seem to be faced towards us. We're looking at it from an angle. And what we can see then is different rings next to each other. So we're actually looking at it from an angle, and then we see different rings. But for most of the rings that we see here, they seem to be faced towards us. So it may be that it's sort of material that is in this direction, but we really would need spectra of all those features to definitely know what's going on.
Okay. Oh, I think wrapping up with the green monster is a good way to do it. Thank you, Ilse. Thank you, Danny. Thank you, Jeonghee, for telling us about this amazing object. Beth put a link to the paper in the chat, and if you go to the SETI Institute website, there is a press release that has all of these lovely images contained in that. This is a production of the SETI Institute. We are a non-profit organization, so we would love it if you would like to get involved. Please sign up for our newsletter, and if you're interested in helping support the research that we do, go to the URL that is down the bottom of the page now. We will be back soon with another SETI Live, and would very much welcome the three of you back at some point in the future to talk more about this object and any future discoveries you make. So thank you everyone for tuning in, and we'll see you again soon.
Thank you.
Thank you.
Thanks.
Bye.